Hello, everybody. Today, our team will present to you the Tacoma Narrows Bridge case study. Our team is comprised of 5 members: Juan Martinez, Amelinda Reyes, Ricardo Cepeda, Jorge Muñoz Cerda, and Joanne Sanchez. This is a brief outline of what our presentation will consist of. First, we will begin by doing some background, then move on to the design of the bridge, then some of the features on the bridge, then the people involved in the design of the bridge, the beginning and how the design of the bridge started, our different ethical concerns, our solutions to those ethical concerns, and using the framework as a guide, and finally, our conclusion. The Tacoma Narrows Bridge connected Tacoma and Seattle. It spanned nearly 2,800 feet and at the time was the third longest bridge in the world. It was opened July 1st, 1940. Clark Elbridge designed the first proposed Tacoma Bridge. Leon Moiseev then took over the project and became the lead and final bridge designer. Clark Elbridge's initial designs for the bridge were a typical suspension bridge with 25-foot high trusses underneath the road to stiffen the bridge and keep it from swaying too much. However, the $11 million design proposed was costly. Engineer Leon Moiseev contributed with a unique and aesthetically pleasing design that replaced the trusses with 8-foot high plate girders, lowering construction costs to $8 million, but providing much less resistance to bending and twisting. The cheaper, slimmer, and more elegant design won, and construction began on September 27, 1938. There were problems even while the bridge was still being built, with the deck moving up and down vertically in even moderately windy conditions. It prompted construction workers to dub the Galloping Gertie Bridge, inspired by a popular saloon song. When the bridge opened on July 1, 1940, the public experienced firsthand the vibrations of the Galloping Bridge. Moiseev's $6.4 million design replaced Elbridge's. It was a 2-lane bridge with two 1,100-foot side spans, and it was designed for 120-mile-per-hour winds. This appearance was known to be of great importance to designer Leon Moiseev. This bridge featured a narrower, lighter, and more flexible design compared to other bridges. However, once built, oscillation was seen in the bridge. These oscillations were actually known and attracted thrill seekers. The structural integrity of the bridge was not questioned, however, as the designer was well respected and the design adhered to safety standards of the time. After it was built, several measures were implemented, but they either failed or were just ineffective. The bridge collapsed on November 7, 1940. It collapsed because aeroelastic flutter caused by high-speed winds plus the natural frequency of the structure. The structure entered resonance, which is an excitation frequency that matched the natural frequency of the structure. Wind was forced to move above and below the structure, which led to flow separation. And this flow separation then led to vortex generation that matched the phase of oscillation. Vortices generated enough energy to push the girders out of their position. Here you see some GIFs of the bridge collapsing. Moiseev's deflection theory laid the groundwork for decades of long-span suspension bridges as they became lighter and narrower. At the time, they were used since it was cheaper because they used less steel. Within this theory, Moiseev entirely overlooked the importance of aerodynamics. Moiseev took a gamble in designing a longer, sleeker, and less expensive bridge by pushing the limits of technology. He, however, was not lucky, and what could have been a breakthrough in technology turned into catastrophic failure. Every time engineers push the limits of technology, they risk a similar loss, sometimes even a loss of life. Fortunately, in this case, no people died. However, when is a possible advance worth the risk to public safety? The stakeholders framework. One way to analyze the ethical concerns in this disaster is to look at who the stakeholders were and what they wanted. First, we have the investors. Even though they already had a design, they chose to change it because a new one was less expensive. Then, there's the designer, to whom the bridge's appearance was personally important. Moiseev even dubbed it the most beautiful bridge in the world. Also, as an engineer, a desire exists to push for new technologies. And finally, the general person would be using the bridge wanted safety. Most of these requirements oppose each other. So what is a proper way to balance them? We argue that investors should not have so much power over negotiations, so that a lot more consideration would have gone into the safety for all the stakeholders. The desire for less expensive designs or for aesthetics should never override the need for safety. The new, less expensive design should not have been accepted in the first place. However, even with its implementation, several things could have been done better for the sake of safety. Transit should have been stopped, as allowing it to continue over a bridge that oscillated like that is too much of a risk. Also, given that several fixes were implemented, they should not have allowed transit until an effective solution was implemented. There is also an argument to be made on the fact that the design adhered to safety standards. However, if one can adhere to safety standards and still cause a catastrophe, a point must be made. It is absolutely not enough to just settle for what is required by standards. Engineers must strive for excellency, following aspirational ethics in order to prevent these disasters from happening again. Additionally, even though pushing for new technologies might necessarily be wrong, given the correct measures we're taking, the way it was done here is especially alarming. In order to push new technologies, there should have been enough evidence in the form of theoretical knowledge or experimental. However, at the time there was no recognized theory in which a design could be based on. Moreover, no bridge of such dimensions existed, but neither of those to support the design. Modeling technologies could have been used, but they were made only after it was seen that the bridge oscillated. By the time they were finished, it did not allow enough time to implement solutions. The ethical issue of values in technology was that the value of convenience was incorporated into the construction of the Tacoma Narrows Bridge. Financing the bridge was an obstacle for Washington State. This is the reason behind why the bridge had an innovative design rather than the originally proposed trusses. Since money was tight, the state was frugal when it set of funds aside for the project. The bridge was constructed focusing on the value of convenience, both economically and aesthetically. This value should not supersede the value of safety. Fortunately, no casualties came as a result of the collapse of the bridge. However, the state should have been more invested in the citizens' safety, even if that meant more money would be spent. It is ethically immoral to willingly put other lives in danger for the sake of convenience. Learning from the failure. An advisory board on the investigation of suspension bridges convened from 1942 to 1954 to better understand and identify design measures to counter the aerodynamic effects of wind. The failure of the bridge caused a worldwide response by bridge engineers to evaluate other existing suspension bridges. In conclusion, the Tacoma Narrow Bridge case study is an example of an ethical problem brought about by an oversight from engineers. There were many concerns during the building process and after the opening of the bridge. Moiseev's attempt to push engineering to its limits was a gamble that ended up costing him and others. This incident allows us to learn about engineering disasters and the repercussions of taking shortcuts. Engineering is used to meet the demands of society, therefore it must be efficient and cost-effective. This demand can lead to shortcuts that reduce the cost of fabrication, which can cause unexpected failures. Engineers are tasked with the ethical duty of fulfilling the needs of society, with public safety and the wellness of society being in the forefront. In the pursuit of innovation, to reduce the cost of technology, the strive for public safety is to be considered before the implementation of said technologies. This case also shows us that sometimes taking too many risks can cause one's career, as Moiseyev's career ended after the collapse of the Tacoma Bridge. About 3 years later, he passed away from his diminishing health conditions.